Okay, I want to thank everybody for joining us for today's session entitled Beyond Audit Logs, a New Approach to Making Lab Data Traceability Easy. Today we're going to be joined by Nathan Clark, co-founder and CEO of Ganymede Bio. I'll introduce him in just a few moments. We go to the next slide. Before we get into the presentation materials, I just want to take a moment and explain a little bit about who Astrix is. If this is your first webinar, we welcome you. If it's a return, we're glad to have you back. So in terms of who we are as a company, a couple of quick facts about Astrix. We are a professional services firm. So we go take a step back to that previous slide real quick. Great. We're a professional services firm, and we've been around for over 25 years. We work with a lot of different technologies in the life sciences space. We don't align with any one. We have a large stable of great partners like Ganymede that we work with on a regular basis. We operate in the US and overseas, over 1,200 employees. 90% of those hold advanced science degrees, which we're very proud of. We're a science-based company that helps science-based companies. And we help companies everything from startups to Fortune 1000 to life science enterprise, chemical, CPG, virtually anybody that has a large R&D presence. That's a company that we can go in and help. So that's just a little bit about who we are. The type of services that we work with, and we go to the next slide, please. We like to say we offer end-to-end service offerings that accelerate digital transformation and optimize performance across your entire technological ecosystem. So this is everything from early stage, where we can help with strategic innovation projects, enterprise architecture, design and development projects, which oftentimes will result in some sort of a roadmap, which is, how you're going to get from where you're at today in technology to where you want to be. This may include us developing RFPs and helping you select different types of technology solutions. We can help implement and develop those solutions. When that's done, we could go through the process and help or just fully validate those systems up to FDA standards. We could provide ongoing application support, whether that's on-site, nearshore, or remote. And then we have an entire wing of our company that handles staffing. So we can do technological staffing, and we can do scientific staffing, which is a little bit unique to Astrix. So a nice little piece there. We can help you with personnel if you are short on that. So that's just a little bit about who we are. We'll go to the next slide. And I'd like to introduce our speaker for today, Nathan Clark, is co-founder. He's the CEO of Ganymede Bio. Nathan, which is Ganymede, which is the modern day data and cloud infrastructure platform for science. Before this, he was a product manager for several of Benchling's data products, including the Insights BI tool, machine learning team. And before that, Nathan had a background in machine learning and data systems, both across general technology, financial technology, and where he is today, obviously, with life science technology. So pleasure to have you on with us, Nathan. I'm going to sit back and enjoy the presentation, and I'll come back on at the end and help with some questions.
Sounds good. Thank you so much, and thank you for having me. Very excited to present today in partnership here. So as was mentioned, we are a data platform for the life sciences, specifically really focused on connecting data workflows in the lab, from lab instruments to applications like ELN and LIMS systems to CRO, CDMO data, you name it. And through that, I think we get to have a pretty unique vantage point on data-related topics, how to structure your data, how to think about data strategy investment, and things like traceability. And that's what we wanted to chat a little bit about today, because I think for a lot of people, traceability is not always the first topic that's in their minds day to day, even on the data management or informatics side. It's oftentimes lumped in with a lot of quality work that can come up later stage in the context of things like GXP or IND filings. But it's something that gets us very excited because it's a very fundamental thing to how you track and manage your lab data. And for us, traceability, of course, is a bedrock aspect of quality, but it also helps so much when it comes to things like experiment debugging, finding data, making that process smooth for your scientists in your lab, driving insights from your data, and ultimately driving automation. Because to us, traceability is one of many aspects of metadata management and how you manage your data. And that's why I want to include this graphic we have on the right, which is a little bit complex and messy, but this is our web of data, web of metadata and associations and context. We're all about data contextualization and traceability of saying, I know for this given data, these scientific results, where they came from, what the original data set was, how they've been modified, if at all. That's a really key metadata and context factor for results, one of many. So beyond the pure quality aspect, there's huge scientific dividends and operational dividends to be had here too. And our argument that we're going to make throughout this is that quality and automation and scientific insights go hand in hand as technology increases. It all converges on having just better, cleaner data structure that can enable all of the workflow automation and visibility that people need. So what is traceability? Lots of different definitions out there, but from our perspective, fundamentally, it's about saying, for a given data set, do I understand where it came from, how it's been modified by who, if at all, when, every single aspect of that, really being able to trace where the data came from, how it was analyzed, if it was analyzed correctly, if it was analyzed incorrectly, if it's been modified correctly or incorrectly, tracing to original copies versus separate analysis one-off copies. And that's a very, very core function of any sort of larger scale quality function, as well as being able to actually just debug experiments. So the workflow that we often see that companies converge on over time is separating out raw data from processed data from final analyzed data. And everything starts with raw data in the context of a lab instrument, which is a lot of what we work on at Ganymede, automating the data flows of. You'll have the lab instrument producing raw data, maybe onto a local PC that's attached to the lab instrument. Someone will manually go into the PC and file that file, organize it in some shared folders or something like that. Maybe you have it automatically uploading to something like AWS or Azure. And then that data will then be consumed by the scientist and processed, maybe cleaning some of the data up or doing some preliminary analysis or point exclusion of outliers, things like that. And then finally, you go through the final analysis of saying, okay, now I can do some statistic on this that's actually going to turn into a scientifically relevant data point, something that's decision ready. The canonical example of this is something like high throughput screening, where you have plate-based data, you get it, you clean it up, you exclude outliers, and then you might do something like a dose response curve fit and get those curve fit parameters out and give something like an IC50, EC50 value that actually goes into your system of record, like an ELN or LIMS. And like we mentioned, to us, this is an aspect of metadata. This is an aspect of having some system in some way to actually relate all of these different steps along the way into your web of metadata. And this is, I think, an unusual perspective because people don't usually look at the metadata in scientific data management side in the context of traceability. To them, traceability is more of a time-based thing, whereas metadata is more like a data association relational thing. But all of this is just aspects of the process. So we're very, very big on saying, similar to how you would think about contextualizing your samples or results or whatever it may be that's your core unit of account in your lab, all these data sets also that you have, your raw data, processed intermediate data, those also should have metadata links on them to the rest of this web. It's very important so that they actually can be tied in, because one aspect of traceability is saying, okay, well, the traditional view, where did this data come from, who modified it and when? But scientific insights can start coming in when you say, well, I know for this final result, it came from this original data set, which was done in this room that was too hot because the HVAC system went off, and I have the environmental data too linked in here to be able to understand why. It all goes together hand in hand. A few words on the evolution of traceability over time to start really digging into this. Traceability has been something that, although the term is more of a recent thing in the recent decades, people have always understood in manufacturing and careful regulated production, where it's very important to store true original copies of data, going all the way back to very early certificates of analysis and sign-offs and batch records well into the late 20th century. That notion of retaining information and document retention was critical. And as things moved into the electronic form, all of these principles carried forward. So things like review and signature processes, tracking metadata, which again, in also a paper batch record manufacturing world, which is where a lot of these principles evolved before the modern level of automation that bench science has gone to. You have people filling out lots of fields of data on their paper batch records, maybe aggregating them centrally. In very high scale manufacturing in the 70s and 80s, you might have something controlled with some sort of a mainframe that'll also be able to actually store some of this in a database through data entry. But then as we move into the 90s and move into PC workstations being ubiquitous and files being a ubiquitous and liquid thing, now you start seeing the introduction of files as the key unit of data traceability. Things like SDMS emerging in the 90s, scientific data management systems, really locking down files and helping ensuring electronic true copies or true originals. And then later on, some of the first paper on glass systems that allowed people to have electronic batch records, electronic lab notebooks now start emerging in the late 90s, early 2000s, LIMS systems, of course. And those also started gaining more unique to electronic system structure that enable traceability. Things like audit logs. Audit logs are something that really only work in an electronic world. You can certainly log events that happen on paper, but you're not going to be able to see everything quite the same way in terms of accesses and data modifications the same way without the electronic context. So audit logs are an innovation of the electronic world. But now, where we are in 2024, people increasingly are using more and more modern tools, electronic tools that are fully digitally native and are designed from the ground up to leverage what you can do with software, having branching workflows and really complex customizable data structure. And what we're going to argue a little bit today is that audit logging is a very useful paradigm, but traceability really to us, the gold standard of traceability that you can get to is going beyond audit logs and even into saying that every aspect of traceability is metadata that's captured in a full relational data model enabled through data automation. And to motivate this a little bit too, let's talk about some of the challenges in building traceability and building out metadata management. Going from the right side to the left side, starting with some of the more human side challenges, traceability always requires more process, more overhead, more metadata tracking and friction. The change management itself of getting people to follow the new processes and understand them can be quite a lot of work, as well as managing the data friction. Asking people to fill out more data, more metadata on everything they do can be slow. So that gets into the process design aspect of this too, where as you think about, okay, what metadata do you want to capture and why? What do you need to feed traceability here? What is worth it? That process design, the value analysis and business case, and the actual physical mechanisms of how people are going to capture the data are more of a process-oriented thing that gets quickly into the technical side and can be difficult. And then as you go further and further towards the technical side of the challenge space, data strategy and structure design can be a big one. If you want to capture data in a structured format, and if you want to drive traceability and have it be something that's truly linked into that web of metadata, like all the rest of the metadata, that requires understanding and thinking about what the metadata you want to capture is. And then similarly on the data lifecycle side, you have to think about what the states that your data exist in are. There are a lot of great standards out there and a lot of best practices to follow for data lifecycle tracking, but ultimately everything does rely a little bit on what your specific process is. And although documents go through different phases, what you need to track about the documents at each life cycle stage can be unique. And finally, all of that feeds into both picking the appropriate software tools and then the most technical challenge of all that we'll talk a little bit about from our perspective is how do you actually thread through metadata? It's one thing to just ask people to label every single data point with metadata required to link it back. And that's a lot of where once people are in sufficiently large scale manufacturing context, you can ask operators and technicians on the factory floor to fill in as much data as they need. But if you look at more of a lab bench perspective or early stage manufacturing process development perspective, that's where there is actually a little bit of friction in how much metadata, in how you capture the metadata when it comes to asking people to track it and manually look at it. So that's something where we see data automation being a solution. So talking about metadata threading, because to us, this is a little bit in the weeds, but it's so fundamental to thinking about how do you establish traceability as a metadata concept rather than as something that's more of a just log-based, event-based, this happened concept. Like everything, you need to be able to thread through metadata through each step of what you're doing, from the raw data to the process data to the final data. And looking at early stage companies, oftentimes, when people start, they just don't track it at all. They're not saying, oh, I have, I'm relating this data point or this unstructured text I'm putting into my ELN back to raw data. They just have the data stored in files on Lab PC. And as people scale up, they might start saying, okay, well, let's build out a central shared drive. Let's start putting things in S3 buckets or something like that. And we actually do need to save all of our data sets so they're not on the lab PCs and they're actually accessible to everyone. We call this the sneaker net as a contrast to internet, because that's where you have people physically going around into the lab, going to these lab PCs, maybe even pulling out USB sticks to move around files and try to get them onto their own PCs, their laptops, into a shared drive, into systems like Box as a more simple file storage way to track things. And that's a good step forward. The data is now at least accessible, but it's still a far cry from being able to actually associate it. And usually in this stage, you have people manually entering in metadata into file names. File name metadata capture is a huge popular thing where people will always say, okay, this file, everyone's SOP is that they need to fill out a sample ID into the file name, which is a good step forward, but is also a little bit of an indicator of, okay, well, that's overloading what the notion of a file name is, or you'll have people encoding metadata into the structure of the folders that they put things in, which is just very fragile and there's a human error. So as you scale up further, many applications through integrations can get to the point where you say, okay, these applications actually let you say that this scientific data point came from this file. Maybe I'm annotating that result with a file name in a push kind of way, or I can pull it in. I can say, okay, given this result, now I can go see all my files and I can say, okay, this file is associated with this data point, which is also helpful, but still requires a fair amount of manual work. Now you're, rather than just writing a sample ID into the file name, now you're picking a file for a sample, but it's the same kind of workflow. So the bottom three options here are all more automated ways to do this, or more structured ways that don't involve people actually having to touch files directly. And I would say the important level to get to is, what does it take for people to not have to touch files? One method is heuristics, saying that during some time period, if the experiment was during this time period and use this instrument, any file that came off the instrument is associated with that experiment. That's not a perfect thing because it might not always be true, but it gets you much closer. You can also do an exclusionary lock on the instrument and say, okay, during this time period, I will by default only let any data that comes off this instrument flow into this sample or experiment or something like that, so that it kind of forces the issue of making sure that that instrument's only used for that experiment. But still, all of these are artificial methods and measures. The gold standard in our mind is what we call the circular automation workflow, where you say you want to have the instrument, when it produces the output file or the output data set, or you're querying its API if it has one, to have that key metadata that you want to link on. You want to have the metadata already threaded through into that output. And to do that, you need to also have the metadata in the input to the instrument. So if you're kicking off the instrument via its API, if it has one, if you're supplying a plate map file or a config file to the instrument as an input, and you can do that automatically, then it already knows the metadata. And now your metadata is fully, truly automated and moving through, and you're not using any sort of human error or proxy for how you're determining that that file goes to that experiment. It's literally on there encoded in the data output. So that's a gold standard to us. And to reiterate that from another perspective, we'd like to talk about the progression of different software systems over time, moving from paper to paper on glass to more modern structured apps to true automation. And what's interesting to us, I would say, is that when you move from paper to paper on glass, a lot of that is motivated by paper's a lossy form factor. It's not centrally viewable. It can be damaged and destroyed very easily compared to software systems. It's not as ergonomic as typing things in or picking from a pick list or things like that. So moving to paper on glass is an important first step. But then you're still kind of replicating the paper process. You're not necessarily leveraging the UI features that you can have in built from scratch software system. So more modern structured apps, I would say modern LIMS, modern ELN systems, have much more data structure and branching workflows that allow you to really optimize the front end of the user workflow through software. But still, all of this is still back into that vein of having people use heuristics or manually indicate what data goes where and manually indicate the traceability. These, all three of these leftmost items here are still requiring human input. They're still requiring a human to say, this is how the data is associated. And that is what we need to excise from the process. So that's why, in our view, the final stage of this is to say, what would it take to establish traceability with zero human input? And the answer is having the workflow be fully automated. The requirements to say that you can automate the full data flow here of automatically supplying the instrument with the data it needs to kick off. Someone just presses play on the instrument, or maybe even it's kicked off automatically, and then any output data from that instrument can be automatically analyzed and put back to where it needs to go in the batch record or ELN or LIM system. That gets you to the point where you truly have zero human input on data association or moving data around. And so that's one of the seeds of what we're trying to persuade folks here of, is that automating the workflow and saving people time is actually also the best way to minimize human error and also maximize traceability and maximize data context. Back to that circular traceability model a little bit as well. This is a slide that we often show about how this works in Ganymede. But no matter what systems you use, you can establish similar principles. If you have your LIMS or your ELN or batch record or workflow system on the upper right, the ideal workflow is to have someone actually start by defining, okay, here's the experiment, here's the batch I need to run, I'm going to define this in my system. And then when I define it, that actually triggers an appropriate configuration file to be put onto the instrument. For Ganymede, we oftentimes receive this as triggers that we get as events, or we'll query the software system to get information. And then when we get that information, we'll load the appropriate file onto the instrument so that the instrument can know what metadata it's running all this in the context of. Instrument runs, our agents acquired the data automatically off of the file and put it into the cloud. In this case, you can see some example files where we have both files that we've acquired from instruments and LabVantage tags with plates that were used. We will actually extract data structure from the LIM system or MES or ELN and say, okay, these are the options for what you want to associate your data with. Maybe you want to associate the data with a plate, maybe you want to associate the data with a sample or an assay, whatever it may be. We can add that on as tags because we have this structured metadata approach to associating files with metadata. And then also when that data is parsed for the processing, and then when that data is analyzed for scientific analysis, all of that is linked through code steps that allow us to say, here's where this process data came from. It came from this file. It's all also linked into that LabVantage plate still. And it's fully reversibly traceable. Any data point, you can always go back to where did this come from, when, what code or logic or user analysis changed it. And then the final data point will flow into the ELN or LIMS or MES system, but all of the lineage before that is still captured and available in Ganymede, or we can send all of that data into client's data infrastructure if they want to put it in their cloud. A few other notes as well. So we are obsessing over this notion of how you automate data traceability and metadata flow through lab instruments. So let's just keep obsessing a little bit further. This is our paradigm of how we think about lab instrument integration, what it really means. And there's 3 layers. One is network integration. How do I acquire the data off of the lab instrument? And also, if I can, how can I provide the lab instrument with some configuration file to kick off? So that comes down to things like our Windows agents we'll install on PCs. People could also have a way of supplying that through a network drive or something like that. Either way, you need to get the data off the lab instrument and have it in the cloud, have it in a way that is accessible for data integration and automation systems. Once you have that accessible in the cloud, then it needs to be parsed. We can't have data in different formats that are inaccessible and not comparable. Every different brand of plate reader, every different brand of chromatography system, you name it, they all have data in different structures unnecessarily. And so mapping all that data into a single consistent structure is the data integration level in our mind. And that's where our connectors come in, as well as at the analysis and transformation level. The final stage is the semantic integration. So great, you have parsed raw data, it's cleaned up, but what do you want to do with it? This, I think, is the final step that we haven't seen most folks in the industry get to on the automation side, because there's been a lot of push and interest in building out a data lake, but it ends up stopping at the point where you have raw data in a standardized format. And that's great. But if you haven't used that data yet and you haven't done something with it, that data kind of sits there and rots in a way. It's very difficult also without the context of how the data is used, or without traceability forward into where this goes in terms of samples or experiments or things like that. It's very difficult to derive centralized insights too. That's a sort of an issue right now in people's attempts to build out high-scale AI and machine learning solutions on this data, is that it just doesn't have enough context. And to us, that context is established through using it. It's established through analyzing it automatically and then putting it where it needs to go in the ELN or LIMS or batch record, because then you have a batch ID, a sample ID, an experiment ID that you can tie all of this to, and there through that you can join on, okay, well, what program is this a part of? What were the experimental inputs? All this additional configuration information, which is really rich that I showed in that first slide with the web, can now be linked on. And that's crucial for both traceability up to statistical analysis, meta-analysis, all the way up to AI and machine learning. They go hand in hand. So that's where we see best practices here at each stage. I would say one of the most important aspects of establishing traceability actually nowadays is choosing integration-friendly instruments. Do your instruments have data coming off in a clean and accessible format that can be networked and can be parsed in a clean way? Are the instruments actually connected to the internet at all? Not the public internet necessarily, but some internal system or some internal network layer on your end that allows them to communicate with your software. And then here also, you have to anticipate that people for folks on the manufacturing side, the ISA 95 framework, for folks not, it's normal to assume that raw data flows into high-level process data that flows into high-level analyzed data. But you might also have things skipping around and jumping. You might need to establish linkages that bypass the traditional data lifecycle and flow. And so you have to also anticipate that all of this data does need to be in one data environment so that you can bypass the linkages and build broader associations than just assuming everything can only see one step forward, that raw data can only ever see what process data it became. Rather, I would say every single node in this graph needs to be able to see every other and read as far down as you can. On the data integration side also, becoming more computer literate and data and automation literate on the scientific side is actually quite important. In smaller labs that may actually warrant scientists being empowered to write their own code. And in larger labs, of course, that's not feasible. And in regulated environments, that's not feasible. But having embedded teams, embedded developers that can support this is quite important. As well as choosing your common data formats, perfecting your limbs, choosing the data structure that you want to use throughout your lab and user tracking is quite important. And then finally, for semantic integration, also on the flip side, not just instruments, but also applications. It's quite important to look at what the integration interfaces are, like clean web APIs are for software that you use, because if they don't have integration touch points, it's going to be much harder. It's going to require a human to go in to establish data traceability, and automation won't be possible. So backing up a little bit here to one of the distinctions that we're trying to draw here is context versus standardization. Both are quite important, but I think standardization is something that is a little bit more common now in the industry, where people really focus on saying, okay, I have data in different formats, maybe I can parse it, maybe I can standardize it into a common data format, or I just have standards in general for what types of file formats I want to use to store my data in. That's very important, but again, without the context, without some of this traceability or other types of metadata, it can be quite tough to understand what the data actually means. So in this case, we have a little example here of your raw data. You probably also want to know what instrument it came from. And maybe the instrument seems like it's out of calibration, but actually the instrument's very hot because it's in the window and it has the sun shining on it. So temperature data also, that's an important piece of context that's almost never tracked and almost never in our experience associated with any sort of scientific results, but is actually quite impactful and meaningful in a lot of cases. It's oftentimes in process development, one of those hidden secret causes that seems like of experiment issues. It seems like animal spirits in the experimental results for this one instrument, but there is a real rational reason. It's just that it's not tracked, and the data is not traceable through to the temperature, for instance. So hopefully that helps explain a little bit of our paradigm, which is that to us, quality, traceability, AI readiness on the other end of the spectrum, it's actually all the same thing. It goes hand in hand. Building out these rich contextualized data sets that are both required for an AI to use and analyze, and for a human to use and analyze in a quality context, they are in many ways one and the same. And as we become more and more scaled up on the digital side as an industry, it's all converging towards this notion of everything really is just relations in a database. And the question is, can you relate data point A to data point B? And so what we see, we have this data pain curve that we like to talk about, is that in the old world, in the current world, really, as your process matures, you're going to be asking scientists and operators to capture more and more and more metadata. And that's because you now know what metadata you can track, and you want to track it. You want to track this as quality parameters, for instance. And that's important, but it can create friction as you scale up, and people don't like that. They have to be spending all this time on data entry. And that's what we love about automation, is that automation allows us to completely invert this. Now, through automation, as the process matures, you can automate more because it's stabilizing. And so time is saved for the scientists and operators, and you as a central IT informatics quality team can also be getting more data than ever before. Now your motivations are hand in hand. You're on the exact same page and wavelength as the scientists on the factory floor or in the lab, which is really cool in our mind. And that helps you move up the data maturity curve. So I love also showing this graphic, credit to Databricks. But this is for general analytics, and I think just as much applies to the life sciences and some of our particular terms that we like to use. So as you move up the analytics maturity curve, and you have to walk before you run to get to that point where you can be doing true AI or machine learning on this data, you always start with saying, do I even know what happened? This is kind of the basic traceability. Are you capturing data? For us, it's using systems of record like ELN systems, LIMS systems, MES systems, maybe quality systems or workflow systems. But the data needs to be somewhere. But then the next question is, why did it happen? Can you actually relate between your data sets? And that's where getting into integration, getting into data warehousing, and simple analytics tools is quite important, because that's where you can start systematizing the data linkages between all of these things. And then you move up further and say, okay, now can I create statistics on this? Can I predict what could happen? Can I extrapolate these data sets out? This requires scale. This requires analysis. This requires data science tools like analysis notebooks or visualization tools. And then finally, you can use that. Once you're running basic statistics on your data, and you have the ability to do that, I always tell people, if you want to go on the digital journey towards AI, first ask the question, how can I do linear regression on my data? Which is kind of a simple artificial thing, but then it begs the question, is the data actually ready? Is the data present to be able to be consumed by an AI model? Then you can get to the point where you can build out digital twins of your lab, you can build out automated design of experiment systems, or even true AI. And every single step of this, I think it's interesting, is all about that metadata context, building that linkages, and driving traceability. So that's where we see the business case coming out ultimately is, one is saving time, and scientists, especially in later stage contexts, can spend a tremendous amount of time doing data tasks, whether it's data entry into these systems of record, moving data around manually themselves in files, doing repetitive analysis in Excel or analysis tools that could be automated. You can probably shave off as much as 20% of their time. That's what we found in many cases, is they're spending 10, 15 hours a week in some cases doing various data tasks at their PC that aren't creative things. And a lot of that can be automated. You also improve data integrity in the process. This is the basic aspect of traceability, which is saying, can I remove the human error? Can I see what happened to diagnosing an error where it exists? Can I reduce the distance of my experiment data and time? How long will it take for me to go find experiment data for a given data set? And then from there, that forms that basis of more advanced analysis and insights. And this is a little bit harder to quantify because it's unknowable. It's a little bit a function of your particular business and context. But that's where you can say data science can start contributing value to your scientific and operational processes. And that also drives efficiency. So the other aspect of all of this is time savings, and then saving money on consumables, doing fewer instruments runs, not needing to buy more lab instruments. That's also a huge aspect of this, if you can actually see how the lab instruments are being used. So to wrap this up, before we go to questions, I want to give a quick word about Ganymede and how we think about this problem. So hopefully from here, everything that I go through a little bit on what Ganymede looks like makes complete sense. To us, the necessary evil that needs to be solved and bridged over here is the human middleware. People doing that manual data work, doing manual file movement, manual file contextualization and data associations, doing that thing of writing, sample IDs into file names, the repetitive analysis, the manual data entry. This is what links data in your lab, whether it's the data movement or establishing traceability. And it's better than not doing it, but it's definitely a far cry from what it could be. And that's why for us, in these same three pillars, we want to take the data source data, automatically get it, automatically build a scientific data management system out of it. But then also we have our core technology called Lab as Code that allows us to have these very robust, flexible, templatized connectors to parse the data, analyze it, do what needs to be done with it, and build these associations automatically, and then put the final data where it needs to go. And as I mentioned, put all of the raw data, process data, final data, all linked together into your data infrastructure. Our integration paradigm follows those pillars that we showed you of how the lab instrument data is eventually knitted into where it needs to go. So our network integration capabilities for data capture, we have a billion ways to connect to things, but the primary use case is our Windows agents, where these are executables that'll actually sit on a PC, and they can do everything from simple file watching up to more advanced things like hitting an API or communicating with COM objects. Once we have that data in Ganymede, we have a large library of connectors that we can use to parse the data, do basic statistics on it. Many types of data you can automate some of the basic analysis or QC steps. And then finally, it's the semantic integration. This is always completely custom to every client, but through Lab as Code, we're easily able to take this data and say, okay, I have my, let's say, IC50s. Now, where do these go? Where in the ELN or LIMS system do these need to be mapped to so they can be automatically populated? And automatically populating that end result with the full context, I think that's the superpower, because that lets us then tag all of the data with the final sample, wherever that data went. And it lets us actually truly end-to-end automate the scientific workflow. So we're not just building out a data lake. We're also putting the data where it needs to go to save scientists time. And through that, we have a richer, more contextualized data lake. And just to show again, these the integration taxonomy on the left in blue, these are all the aspects that Ganymede covers. We try to say everything from the instrument to where the data needs to go. We have the complete solution to fully automate the data. And that solves traceability, and that solves building out a fair data layer. But that also is an engine for automation. And again, that notion of automation going hand in hand with fair data and quality comes to the forefront. We also see this, like we mentioned, we oftentimes use this data and we'll build this data set in service eventually getting to the point where you can do true AI or machine learning. And I like to use this example of a work cell. If you think about a liquid handler or a work cell doing predictive maintenance on it, people always are interested in things like, how do I use machine learning or AI for predictive maintenance? But to us, the root of this actually is integrating the right data sources. A canonical example of how to do predictive maintenance is saying, if I'm looking at a motor that's failing, or say a belt that's starting to wear down on the track of the liquid handler, I can look at the power draw over time of the system, and I see the power draw actually starts ramping up as the component starts failing, because the liquid handler will need to draw more and more power to actually be able to drive the system and still make the head move around as needed. And it draws more and more power, and it kind of hockey sticks up until it breaks, and then goes into maintenance mode, and then you fix it and it returns to a nominal level. And if you look at this chart, AI can certainly help improve things and find these things before you notice as a human. But inspecting it as a human, you can also see the issue. Even having some basic statistics on this would be quite helpful. But the root problem behind all of this is that you just don't have the data. It's not connected. The power draw data that you need to get the y-axis going here, the x-axis of time and log data and system of record data, like what samples are flowing through this or how often the instrument's running. Maybe your asset management system will help you find out when things are in maintenance mode, so you know why it's not running and there's no power draw at all. Or the scheduler orchestrator for saying, okay, these are the runs that are happening over time. All of these need to be knitted together to actually create this chart. So it's easy to make promises of AI or machine learning when you're assuming that the data set is ready and available. But to us, the problem is getting the data set there. And then the analysis can flow from there. And so that's what we really focus on powering as a company as well, beyond just instrument to application connectors, knitting together broad data sets across multiple applications and instruments that provide these deeper insights. And that's how we move up this pyramid, our value pyramid of the different 3 layers of what we do. The base level is data capture systems, offering a rich SDMS capability with Ganymede, with our scientific file system, fair data, parse data, our agents, our data governance tools like our tagging systems. The next layer is data automation. How can we actually take that data and integrate it with the ELN or LIMS or MES or whatever it may be that you want to connect that data to. That requires automation, that requires our instrument connectors, that is where our lab as code system specializes. But all of this forms a rich data foundation for the top of the pyramid, which is the managed AI layer and managed analysis layer that all of the stuff above, like the predictive maintenance example, come from. So that's where we get with our highest scale deployments. And that's it. So I appreciate the time from Astrix, and I'll turn it back here.
Great, thank you very much. I appreciate the depth of the presentation materials, Nathan. That's good stuff for sure. Again, I want to remind everybody, if you have questions that popped up during the session, you can simply type that question into the GoToWebinar panel, and we will tackle those questions promptly. Let me do a couple things here real quick. I'm going to go ahead and get the recording stopped.